Welcome to Mech Cosmos, Engineering Explained. On the afternoon of March 27, 1977, the island of Tenerife in the Canary Islands was covered in thick fog. At Los Rodeos Airport, two of the largest passenger aircraft ever built were sitting on the runway, waiting to depart. Both were Boeing 747s, each carrying hundreds of passengers. Both crews were experienced. Both aircraft were in perfect technical condition. There was no reason to expect anything other than two routine departures. At 17:06 local time, the two aircraft collided on the runway. The explosion was visible for kilometers. The fire burned for hours. When it was finally extinguished, 583 people were dead. It remains to this day the deadliest accident in the entire history of aviation. More people died on that runway in Tenerife than in any other aviation accident before or since. And what makes this disaster truly extraordinary, truly devastating, is not just the scale of the death toll, it is how it happened. There was no mechanical failure, there was no bomb, there was no catastrophic structural problem. Two perfectly functioning aircraft, with experienced crews, collided on a runway in conditions that should never have led to a collision. The accident was the product of a chain of human factors, communication failures, organizational pressures, and a single catastrophic decision made by one of the most experienced pilots in the world. This is the complete engineering and human factors explanation of the Tenerife airport disaster. We are Mech Cosmos, Engineering Explained. Let us begin. To understand what happened at Tenerife, you first need to understand why two Boeing 747s were at Los Rodeos Airport at all. Los Rodeos was not the intended destination for either aircraft. It was a diversion airport. The events that led to the collision began earlier that afternoon at Gran Canaria Airport, the main airport for the Canary Islands located on a nearby island. At approximately 13:15, a bomb exploded in the terminal building at Gran Canaria Airport. The bomb had been planted by a Canarian separatist group. A second bomb threat was received shortly afterward. The airport authorities decided to close Gran Canaria Airport while the terminal was searched and any further devices were located and neutralized. All aircraft that had been inbound to Gran Canaria were diverted to other airports in the region. Los Rodeos Airport, on the neighboring island of Tenerife, received a large number of these diverted aircraft, including several wide-body jets. Los Rodeos Airport was not equipped to handle this volume of large aircraft. It was a relatively small regional airport with limited apron space and limited ground handling capacity. The diverted aircraft had to be parked wherever space could be found, including on the taxiways. This parking of aircraft on the taxiways would have significant consequences later in the day. Among the diverted aircraft were two Boeing 747s that would become the two aircraft involved in the collision. The first was KLM Flight 4805, a KLM Royal Dutch Airlines 747 that had originated in Amsterdam and was carrying 248 passengers and crew on a charter flight. The KLM aircraft was commanded by Captain Jacob van Zanten, one of the most senior and most respected pilots in the entire KLM organization. Van Zanten was the chief flight instructor for KLM. He had appeared in KLM advertising. He was the public face of KLM safety. He had over 1,700 flying hours, of which 1,545 were on the Boeing 747. He was by any measure an exceptionally experienced and respected aviator. The second aircraft was Pan Am Flight 1736, a Pan American World Airways 747 that had originated in Los Angeles with a stop in New York and was carrying 380 passengers and crew. The Pan Am aircraft was commanded by Captain Victor Grubbs, who had over 21,000 total flying hours. His co-pilot Robert Bragg and flight engineer George Warnes were also highly experienced. Both aircraft sat at Los Rodeos for several hours, waiting for Gran Canaria Airport to reopen. The delay created a serious problem for the KLM flight. Dutch aviation regulations strictly limited the number of hours a crew could be on duty. Captain Van Zanten was acutely aware that the delay was consuming his crew's duty time. If they were delayed much longer, they would exceed their duty time limits and would not be legally permitted to fly. They would have to be replaced by a fresh crew, which would mean an even longer delay and significant cost and inconvenience for KLM. Van Zanten was under pressure, not pressure from KLM management, but the self-imposed pressure of a highly experienced professional who wanted to complete his flight and understood the consequences of exceeding duty time limits. Gran Canaria Airport reopened in the late afternoon, and the aircraft at Los Rodeos began preparing to depart. Because several aircraft had been parked on the taxiways, the normal procedures for taxiing to the runway could not be followed. The airport did not have a parallel taxiway that was clear of aircraft. The only way to get the large aircraft to the runway was to taxi them along the runway itself, a procedure called back taxiing. The aircraft would enter the runway at one end, taxi along the full length of the runway, and then turn around at the far end to position themselves for takeoff in the opposite direction. This back taxiing procedure meant that multiple aircraft would be on the runway at the same time. The KLM aircraft taxiing along the runway to reach the takeoff position, and the Pan Am aircraft also on the runway, taxiing toward its designated exit point. This was inherently a higher risk situation than normal operations, but it was a manageable situation if communications between the aircraft and the tower were clear and unambiguous, and if all parties had a precise understanding of where every aircraft was and what each was doing. The weather at Los Rodeos was deteriorating. Thick fog was rolling in from the surrounding hills. Visibility on the runway was dropping rapidly. At times, during the critical period, the visibility was as low as 300 meters, far less than the length of the runway. The two aircraft on the runway could not see each other. The controllers in the tower could not see the aircraft on the runway. Everyone was operating entirely on radio communications and their mental model of where each aircraft was on the runway. The KLM aircraft reached the end of the runway and turned around. It was now in position for takeoff, pointing down the runway toward the Pan Am aircraft, which was still taxiing along the runway looking for its exit. The KLM crew began their pre-takeoff checklist. Captain Van Zanten applied power to the engines, beginning the takeoff roll. His co-pilot, First Officer Klaus Meurs, transmitted to the tower that they were at takeoff, a non-standard phrase that was ambiguous. It could mean they were at the takeoff position and ready, or it could mean they were commencing the takeoff roll. The tower controller heard the transmission and responded with an instruction to stand by for takeoff clearance, indicating that takeoff clearance had not yet been given. But at the same moment, the Pan Am aircraft transmitted a radio call on the same frequency. The two transmissions occurred simultaneously. The simultaneous transmissions caused a heterodyne, a squealing interference sound, on the frequency that partially blocked both transmissions. The KLM crew heard only a fragment of the tower's response. They did not clearly hear the instruction to stand by. The Pan Am crew's transmission warning that they were still on the runway was also partially blocked. Captain Van Zanten continued the takeoff roll. The KLM 747 accelerated down the runway in the thick fog. In the cockpit, the flight engineer asked whether the Pan Am aircraft had cleared the runway. Captain Van Zanten responded assertively that they had. He was wrong. The Pan Am aircraft was still on the runway. It had missed its intended exit in the fog and was looking for the next available exit. The Pan Am crew could hear the KLM engines, but could not see the aircraft. When they saw the landing lights of the KLM aircraft approaching at high speed through the fog, there was nothing they could do. Captain Grubbs applied full power and attempted to turn off the runway. It was too late. The KLM aircraft was traveling at approximately 260 kilometers per hour when it struck the Pan Am aircraft. The KLM aircraft had rotated, its nose had lifted off the ground, but it had not yet achieved sufficient altitude to clear the Pan Am aircraft. The lower fuselage and engines of the KLM 747 struck the upper fuselage of the Pan Am 747. The impact ripped open the top of the Pan Am aircraft across almost its entire length. The KLM aircraft continued into the air briefly before crashing back onto the runway, approximately 150 meters beyond the collision point. The Pan Am aircraft was immediately engulfed in fire, fed by the enormous quantity of aviation fuel in its tanks. The upper fuselage had been completely destroyed by the collision. Of the 380 passengers and crew on the Pan Am aircraft, 335 died. The 61 survivors were those seated near the left side of the aircraft who were able to escape through the torn open fuselage before the fire became unsurvivable. Tragically, several survivors who had escaped the aircraft died when they were struck by debris from the burning KLM aircraft. The KLM aircraft crashed and burned completely. All 248 people on board died. There were no survivors from the KLM aircraft. The total death toll was 583 people, 335 from the Pan Am aircraft and 248 from the KLM aircraft. It remains the highest death toll of any aviation accident in history. The investigation was conducted by the Spanish authorities as the accident occurred on Spanish territory. The Dutch and American aviation authorities also participated as the states of registry of the two aircraft. The investigation took several years and produced a detailed analysis of every contributing factor. The immediate cause of the accident was the KLM aircraft commencing its takeoff roll without having received takeoff clearance from the tower and while the Pan Am aircraft was still on the runway. Captain Van Zanten began the takeoff without clearance. This was the proximate cause and it was unambiguous, but the investigation went much deeper than this single act. It identified the conditions that led a supremely experienced professional to make this fatal error. The pressure of the duty time situation was identified as a significant factor. Van Zanten was aware that any further delay might require the flight to be canceled entirely. This created a psychological pressure, even if not explicitly acknowledged, to minimize further delays. When the ATC clearance was received, a route clearance, not a takeoff clearance, Van Zanten may have mentally interpreted it as permission to go in the context of his desire to depart as quickly as possible. The communication failures were identified as a critical contributing factor. The phrase used by the KLM co-pilot, "We are at takeoff," was non-standard and ambiguous. Standard phraseology would have been unambiguous, rolling for takeoff or commencing takeoff roll. If standard phraseology had been used, the tower controller would have immediately recognized that an unauthorized takeoff was in progress and could have issued an immediate stop instruction. The partial blocking of the tower's standby instruction by the simultaneous Pan Am transmission was a tragic coincidence that removed the last opportunity to prevent the collision. The cockpit dynamics were also analyzed carefully. The flight engineer's question about whether the Pan Am aircraft had cleared the runway represented a potential intervention that was dismissed by Captain Van Zanten. This raised important questions about crew resource management, the extent to which co-pilots and other crew members felt empowered to challenge the captain's decisions. In 1977, the authority gradient in aviation cockpits was very steep. Captains were absolute authorities. Co-pilots and flight engineers rarely challenged captains, even when they had concerns. The concept that a junior crew member had not just the right but the responsibility to challenge a senior pilot's decision if they had safety concerns was not embedded in the culture of aviation in the way that it is today. The fog was identified as a contributing factor. If visibility had been sufficient for the KLM crew to see the Pan Am aircraft on the runway, or for the Pan Am crew to see the KLM aircraft approaching in time to clear the runway, the collision would not have occurred. But the fog was not a cause. The fundamental cause was the decision to commence takeoff. Fog simply removed the visual safety net that might otherwise have prevented the collision even after the decision was made. The consequences of the Tenerife accident for aviation safety were as profound as the accident itself was devastating. The disaster became the founding case study for the entire field of crew resource management. The systematic training of flight crews to communicate effectively, challenge authority constructively, and make decisions collaboratively rather than autocratically. Every airline pilot who has trained since the late 1970s has received CRM training that traces its origins directly to the lessons of Tenerife. standard phraseology was dramatically strengthened and standardized across international aviation. The ambiguous and non-standard phrases that contributed to the communication failures at Tenerife were replaced with precise, unambiguous terminology. The phrase takeoff is now used only when actual takeoff clearance is being given or acknowledged. For all other communications involving the runway, the words departure position or line up and wait are used instead. This standardization has eliminated entire categories of potential miscommunication. The concept of sterile cockpit, the prohibition on non-essential conversation below 10,000 feet and during critical phases of flight, was formalized and strengthened. The understanding that distractions and non-essential communications during critical phases are a safety hazard became embedded in aviation culture and regulation. The authority gradient problem was directly addressed through CRM training. Modern CRM emphasizes that every crew member has not just the right, but the obligation to speak up if they believe a safety issue exists, regardless of their seniority relative to the captain. The captain retains final authority, but the culture that prevented junior crew members from challenging senior captains has been systematically dismantled over the decades since Tenerife. Airport surface movement and situational awareness have been dramatically improved. Modern airports use surface movement radar that provides controllers with a precise, real-time picture of all aircraft and vehicles on the movement area, regardless of visibility. Runway incursion alerting systems warn controllers and pilots when an unauthorized presence on a runway is detected. These systems make a collision like Tenerife far less likely at modern airports equipped with current technology. The Tenerife disaster also highlighted the dangers of operating major airports beyond their designed capacity and the importance of having adequate contingency plans for situations where large numbers of aircraft must be diverted to secondary airports. The chaotic situation at Los Rodeos, multiple large aircraft on taxiways disrupting normal operations combined with deteriorating weather and communication difficulties, created the conditions in which the accident could occur. Better contingency planning and operational procedures for diversion situations have been developed and implemented across the industry. Roger Boisjoli, the Challenger engineer we discussed in a previous video, said that the hardest thing in engineering is not the technical problems, but the human problems, the organizational failures, the communication failures, the pressure to perform that leads experienced professionals to make decisions they would never make in a calm, rational environment. Tenerife is the most tragic illustration of this truth in the history of aviation. 583 people died on a foggy runway in Tenerife on March 27, 1977. They died not because the aircraft they were flying in were unsafe, not because the pilots flying them were incompetent, but because a chain of circumstances, a bomb at another airport, a diversion and unexpected delay duty time pressure, deteriorating weather, non-standard communication, a simultaneous radio transmission, and a fatal misunderstanding, combined to create a situation where one of the most experienced pilots in the world made a single catastrophic error. The lessons learned from their deaths have made aviation dramatically safer. The crew resource management principles that Tenerife inspired have prevented countless accidents in the decades since. The communication standards that were strengthened after Tenerife have eliminated entire categories of dangerous misunderstanding. The technological improvements in airport surface surveillance have made runway incursions far less likely to go undetected. That is the legacy of Tenerife. And that is why we study these accidents, not to assign blame, not to sensationalize tragedy, but to understand exactly what went wrong in every dimension so that we can build systems, cultures, and procedures that make similar tragedies less likely in the future. We are Mech Cosmos, Engineering Explained. If this video gave you a deeper understanding of what happened at Tenerife and why, then subscribe, hit the notification bell, and join us for the next video. Because every machine has a story, and sometimes that story teaches us how to make the world safer.